to put yourself to the test and show us the passage of time. We're gonna need a montage, a sports training montage, show that thing.
I'm Adam Hickey.
I'm Nathan Love.
I'm Andrew Yelder.
And I'm Janelle Jones.
And we're Group 5.
AKA
Group Awesome!
also
Trains and stuff and cows.
in cows. We are now going to give a brief overview of our project description. For our project, we were required to track a train's speed, location, and distance or direction of the train on the Sioux Line track. To do that, we decided to use sensors, but we were not allowed to put the sensors on the actual trains themselves. The sensors all had to be on the track, and we chose some sensors, but we'll talk about that in a sec.
The other thing we had to do was display this information to two interfaces, an LCD interface and a web interface. As you can see here, here's the LCD interface on this ARM board that we used for our project.
We also had a web interface, which was a column setup giving the train's ID number set by LocoNet, the train speed, the distance that it was from a particular sensor, and what section it is of the track, which we broke up into sections. To do this, we used 8 different sensors. First off, we had 4 IR sensors. These were set up in the longer sections of the track so that we could get the distance from the sensor, and using a time variable we also got speed from the change of distance. And
We also used photo transistors, tiny little sensors like this, that we put into holes in the track. And when the train drove over these sensors, the change in light, we were able to determine whether or not a train was over the sensor so we could make our algorithms more accurate.
yes, and then all this information was passed along to an algorithm that would determine all of this information and compile it all so that we could pass it on to our displays.
So this is the TEPT 4400 phototransistor that we use for our project. We place them in the diverging sections of the track. The way that these work is when the amount of ambient light decreases, the amount of current decreases. Since we can't directly measure current, we had to put a resistor in series with the phototransistor to give us a voltage, and then we sent that voltage to the PIC, to the A to D inputs on the PIC to be used. This is one of the sharp distance measuring sensors that we used on the straight edges of our tracks. The way this works is it has an emitter and a receiver, and the emitter sends out an infrared light, and when an object passes through that light, the infrared light is reflected off of that object and sent to the receiver. The receiver analyzes the signal, which then turns it into an analog voltage, which we then send to the A to D input in the PIC. For our project, we had to create a PCB that would take the values from the IR sensors and the phototransistors and send them to the PIC. We have 4 MCP 617 op amps and 3 TC 4452 MOSFETs. The op amps act as unity gain buffers to the outputs of all of our sensors, and the TC 4552 MOSFETs are used to turn on our IR sensors using the PIC. Unfortunately, we weren't able to use the PCB because some of the wiring done in Eagle was incorrect. So we had to resort to using a breadboard prototype that had all of the components used in the PCB, and we have it set up so that the PIC can still be programmed and we can still send messages through here using I2C.
I was responsible for designing an algorithm that would take all of our sensor data, including LocoNet, phototransistors, IR sensors, and time, and calculate the location, speed, and direction of all the trains on the track. The first thing I did was create an internal data representation of the track. This is a drawing of the track. Each one of these sections is a node in a graph that I created within the code. Each one of these sections has a section number, as you can see I've drawn them, and a distance. This one I believe was 100 centimeters. This one was 212 centimeters. A train was an object on the graph. As the train moved about the track, we incremented its location. When a new train started on the track, we received data from LocoNet indicating that a new train was put on the track and given its new speed. All of our trains had to start in this area of the track. When we received new LocoNet data, we knew that a new train must be here. We guessed about its original speed from the LocoNet speed command that was sent to us. As the train begins moving along the track, we receive sensor data. We have an IR sensor here that can measure along the straight section, another one here. As the train begins moving around the track, we capture each data point and send it to the algorithm. The algorithm then determines which train that data is closest to. So for instance, if this sensor found a data point right here, it would know that this data point goes to the train that's in the starting location. As the train receives more of these data points along the track, the algorithm calculates a new speed of the train. A timer runs the algorithm. Every time the timer goes off, the train is incremented along the track based on its current speed. Here, we have switches in the track. We know the state of these switches from LocoNet data. Every time a LocoNet switch is thrown, LocoNet sends a message that we intercept, and the algorithm stores that data. That way, we know which direction a train should take around the track. Phototransistors are here in the track. And when the train goes over one of those, we have another data point that we can use to calculate its speed. After all this has happened, the algorithm periodically sends data to the displays, including the ID of the train, the location of the train, the speed of the train, the direction of the train. And that's the algorithm.
Okay. So we mentioned LocoNet earlier, so let me explain it a little. Basically, it is a peer-to-peer distributed network system on which all devices can monitor the network data flow. So when we hook up our PIC board to the actual LocoNet communication, it can see everything that's going on. And the way it works basically is that it's event-driven by different devices in time, and it's not pulled by a centralized controller in normal operation. So if we wanted to communicate on it, we could just say whatever we want, and hopefully it won't collide with anything. And it's just a powerful, decentralized, and scalable distributed system, which is similar to the way that the telephone system works, as well as the internet. So when you think of LocoNet, you can think of an internet for trains. So the part of the project that I worked on is the sensors PIC, which used a PIC 18F2680, and basically what it did was bring in all the sensor data, the phototransistors and the IR sensors, and converted those voltages using the analog to digital converter into a digital value, at which point it sent that information over to the PIC, or over to the ARM via I2C. One of the parts that I designed is the code for the 2680 PIC on our board that reads LocoNet, which is sent from the DCS50 to the trains on the track. And right here is the board that connects up to our LocoNet board and communicates to it via UART. And then what this board does is basically just read the message, package it up into a format we designed, and sends it over I2C to our ARM board, at which point it uses the LocoNet messages to figure out where the trains are, or uses it to find out the direction. And that's it. Here's an example of the web server that we use to display train statistics. Right here we display the train ID, the speed, the direction of the train, the section in which the train is in, as well as what distance it is actually in the section, or how far it is in the section. So as you can see here, you can see it refreshing. It refreshes every second, and the way it works is it's showing the train ID. Right now it's the train 0, and it's showing how fast it's going, which is 37 centimeters per second. It's going forward, and it's currently in section 2. It's probably about to move to section 3. There it is right there. And that's about it. Just shows statistics for the train, as well as while the LCD is running.
Oh hey, didn't see you there. While you're here, why don't I take some time to explain to you what I did for my part of the project. First off, I handled a lot of the I2C communications that come from the PICs to the ARM board through this nice I2C cable. Basically what that entailed was taking the data that was sent over in our message format and then converting it to a more usable format that was then sent along to the algorithm. Basically when the data comes in order to convert the voltages to actual voltages in a float format, I had to take 2 separate bytes and convert them using a method that we came up with. And once we did that, I put in a message and that went to the algorithm. Then the other part of my part of the project was to take data from the algorithm and convert it to a nice little LCD display. Now, I don't know if you'll be able to see, I'll bring it up to the screen here, but basically I have a nice little picture of the track and then little trains that go around the track, and I don't know if you'll be able to see, it's kind of hard to see blue, but this train, if you look closely, is actually blue, and the different trains are different colors, and that's all set up, and you can see the colors on the web display. And so basically as the train goes around the track, the LCD is updated to show you the location of the the train, sorry. And that was my part of the project.
Here's an example of the LCD display while a train is driving around the track. As you can see, the blue train is driving around the track while the ARM is receiving data from the PIC, giving it the information to the algorithm to predict where the train will be on the track as it goes around. And here it is.
It's your prime. That's when you need to put yourself to the test and show us a